Okay, we're going to look at this, what we call biconditional statements. Okay, this is coinciding with section 2.2 of your textbook. Okay, so biconditional statements, a statement that has a conditional and converse statements true and can be written with an if and only if phrase. So again, we reviewed, if we go back from previous, okay, we talked about conditional statements of the form if A then B, okay, if two lines are parallel then they do not intersect, okay, and then we talked about the converse, okay, the converse being if two lines do not intersect then they are parallel. All right, this conditional statement was true, the converse was not. So here again is reminding you of what conditional and converse statements are. Now let's look at the biconditional, as was our intention here. Okay, so we start with a conditional statement. Let's see, here we go. If 3 points are collinear, then they lie on the same line. And we ask ourselves, is that true? Okay. We also ask, what is the converse? Okay. Well, the converse again switches the if and the then. So the converse would be if 3 points are on the same line, then they are collinear. Okay. And we have to ask if that is true. If 3 points are collinear, then they lie on the same line. That is true. If 3 points lie on the same line, then they are collinear. So both the conditional and the converse are true. And therefore, a biconditional, which means the original, the conditional statement, and its converse are both true, then we can rewrite this as an if and only if statement. So the if and only if statement would be 3 points are collinear if and only if they lie on the same line. 3 points are collinear if and only if they lie on the same line. Let's try another one. Conditional statement. If two angles have the same measure, they are congruent. This conditional is true. What is this converse? Converse, if two angles are congruent, then they have the same measure. This is true. Both conditional and converse are true, therefore it can be written as a biconditional statement, which is with the if and only if. That biconditional statement, two angles have the same measure if and only if they are congruent. Well, we could also justifiably say two angles are congruent if and only if they have the same measure. So now we're going to do some additional exercises in writing a definition as a biconditional. Okay, writing a definition as a biconditional. A definition, we knew perpendicular lines are two lines that intersect at right angles. Okay, so as a definition, that can be written as a biconditional, okay, which is if we can identify the if and then components. So here we go. Perpendicular lines are two lines that intersect at right angles. If two lines are perpendicular, then they intersect at right angles. The converse, if two lines intersect to form right angles, then they are perpendicular. Okay? And the biconditional, writing it as an if and only if, would be two lines perpendicular if and only if they intersect to form right angles. Okay? Often we will want to consider if the definition is acceptable. So we consider the following. An airplane is a vehicle that flies. Seems legit, but let's see. Okay? In order to test it, we need to test it. We need to break it down into a conditional and a converse and see if both are true. If a vehicle is an airplane, then it can fly. Okay, true. What's the converse? If a vehicle can fly, then it is an airplane. Not necessarily true. Could be a helicopter. Okay? Or okay, a rocket or any other kind of vehicle that flies. Okay? Nonetheless, okay, what we've done is we've considered something, whether it was a good definition. It's a good definition if we can write it as a conditional and a converse and both end up being true. Since this statement, okay, an airplane is a vehicle that flies, when written as a conditional and a converse, did not prove to be true on both occasions, this is not a suitable definition for this. Conditional and converse here are not both true, therefore it is not a biconditional, which means reversible, which means true both with conditional and converse, and does not serve as a suitable definition. Let's consider another, if this is a good definition. Parallel planes do not intersect. So again, in order to consider it as a proper definition, you want to write it as a conditional, okay, and check its validity. So conditional, if two planes are parallel, then they do not intersect. This is true. The converse, if two planes do not intersect, then they are parallel. So the conditional and the converse are both true, okay, and that being the case, we can accept the statement parallel planes do not intersect as a suitable definition, okay? And it can be written as a biconditional, okay? We have some symbols that we use, okay? Symbolic notation for biconditional statements, okay? A conditional says if A, then B. So the symbolic notation is A, then B, with the arrow pointing towards B. The converse then says, okay, we go from B to A. Okay, this is saying we go from A to B. This is saying we go from B to A. The biconditional is saying that we can go back and forth, okay, which is, again, both conditional and converse are true, okay? So I think that will suffice for what we're going to do in section 2.2. I would review the video again if need be. The topics of concern: biconditional statements, which are statements whose converse and whose conditional and converse both prove to be true, and when that is the case, we can make a proper definition out of it, okay? We'll give you some exercises tomorrow to test that idea.